We're going to start this unit with a relatively short video discussing what modern atomic theory is and a little bit of the background history as to how the current model of the atom that we have came into being. To go through the learning objectives of this video, we're going to start with answering the question, why do we need an atomic model? Once we identify that need, we're going to talk about how this model has developed over time, and then finally wrap up with a discussion of the current understanding of what the atom structure actually is. This discussion is going to be very brief, and we'll go into a lot more detail later on in the unit. Over on the right, we can see a picture we're going to see a couple times throughout this unit, and this is a picture that probably doesn't look very familiar, but is a better representation of what an atom's internal structure looks like than most people think of. A lot of times people are thinking of that model with the rings and the electrons on the rings. Turns out that's not a really great picture. To begin with, let's talk about modern atomic theory itself, and basically the question of why do we actually need a model. So modern atomic theory is a science focused on developing an accurate model of real atoms. And this is really a combination of physics and chemistry. Physicists spend a lot with this, and then chemists obviously are very interested in the outcome. The closer we can get that model to behave like a real atom, the better understanding we get of how atoms themselves work, and ultimately the chemistry that goes along with them. Now these models are going to focus primarily on electron behavior. Earlier in the year, we spent a bunch of time talking about how things work in the nucleus. That is actually fairly well understood science. The electron behavior turns out to be a lot more complex in a lot of ways. Also, electron behavior accounts for a lot of the chemical properties of a substance. So while things can be going on inside of the nucleus, they don't necessarily affect the outward behavior that the atom has towards the other atoms around it. Bonds forming in chemical reactions focuses primarily on electron behavior, therefore these models focus primarily on electron behavior. So getting then into the question, why do we actually need a model itself? If you think about how we go about viewing things in the world, your sense of eyesight works where we have light coming from a light source, in this case the sun. The sun provides us with all possible spectrums of light. This light hits an object. Our object then absorbs many of the wavelengths, and then one of those wavelengths ends up bouncing off. The light that bounces off is the light that makes it over to our eyes. Our eyes then send a signal off to our brain, and we end up seeing the color that gets reflected as opposed to the colors that get absorbed. And that's how sight works. When you want to see something, you're really seeing reflected light. When we take a look at an atom then, and we want to see what's happening in the internal structure, what we can see here is that there's really nothing in here for our light to actually bounce off of. Electrons are too small and move too fast for light to be able to hit those, at least not in a way that can reflect back to our eyes. And the nucleus takes up a space that is a fraction of a fraction of a fraction of the size that the electrons actually occupy. Again, a surface that's generally too small to reflect light in any kind of meaningful way to get back to our eyes. The short of this conversation is that we cannot see inside of an atom with the way we see, for example, a pear, and as a result, to represent what's happening inside of an atom, we need some sort of model to represent that internal structure so we can interact with it as people. Now let's see if we can't get some of that written down on paper. It is impossible to visualize the internal structure of an atom. As we saw in our previous diagrams, there's really nothing for that light to bounce off of, for it to be reflected back to our eyes for us to be able to see. It's not really a matter of not having the right equipment, it's really a matter of the fact that it just can't be done. Therefore, a model is needed to represent that internal structure, and that's the key word we want to point out here, is the idea that we're trying to just represent that internal structure with something we can use to interpret what's going on. Now this model needs to be built from data collected concerning atomic structure. We don't just want to make something up, it has to be something built off of actual observations. As we get better data and better observations, we take older models and replace them with newer models. And typically the new model takes the old stuff from the old model that worked and adds in new components, and as a result we end up with a better picture. And all of this really kind of encompasses what ends up being almost thousands of years of work developing our current understanding of the picture of the atom today. So talking about those thousands of years of work, we can see how the historical development of the model of the atom actually grew. This is something we talked about earlier in the year in terms of presentations you guys did about atomic structure history, but we can talk about this in more detail now. If you recall, the beginning discussion started with a couple of Greek philosophers by the name of Democritus and Leucippus. Not as much is known about these two guys, but they're both credited with the concept of the atom, and then that concept was then codified into science by a scientist by the name of John Dalton. Altogether, they basically discovered atoms, and their atoms were extremely simple. It was simply a small sphere of indivisible material, meaning it was the smallest unit of matter that still had the same properties of the substance as a whole. Basically, their model was simple enough to the point where if you had more of this atom stuff or less of this atom stuff, that's what delineated one element from the other. A very crude model, but a wonderful start to a concept that didn't even exist before these guys came around. The next step in model development came by a scientist from J.J. Thomson. He was the first scientist to discover subatomic particles, meaning atoms aren't made up of just atom, they're made up of smaller pieces still. He discovered specifically the electron, and he created a new model based on his discovery. Unfortunately, this new model, while a better picture of the atom, still had very little to no predictive power, little actual usable science going along with this. If you recall, his model had the name of the plum pudding model. We don't eat a lot of plum pudding these days, but you can think of this as a chocolate chip cookie. Basically, he saw negatively charged electrons, like chocolate chips, embedded in a positively charged goo, which would be the cookie that they're attached to. And as you can see, there's more detail here than there was with the Dalton model. The next step in the development of an atomic model is where things started to get a little bit more interesting. The first part of this discovery came by a scientist named Ernest Rutherford. He was a student of J.J. Thomson's. He was a scientist credited with discovering the nucleus of the atom. He took that general shape of the atom that he had and started breaking it down into distinct regions, places for protons and neutrons, and a separate region for electrons. This work was then followed up by another scientist by the name of Niels Bohr, who we'll be spending a lot of time later talking about. And he took Rutherford's model and outlined it further by coming up with a way of arranging electrons based on this. His model is often referred to as the planetary orbit model, and this is the first model that had the ability to start predicting some properties. We could predict in advance the characteristics of certain atoms based on the model that he created. As we pull up a picture of this model, you can see that this model is something you might be a little bit more familiar with. The traditional nucleus in the center here, although definitely not drawn to scale. Our nucleus in the center here is surrounded by concentric rings of electrons. As we said, we'll talk more about this model later in the path, but this is the beginning points of a real, truly predictive model for our atom. The most recent step in this process is what we describe as the current understanding of atomic structure. And this is a model based off of something known as the Schrödinger wave equation. Basically, new discoveries concerning electron behavior get folded into the description of those electrons, and as a result, we can create a better prediction of what electrons do, resulting in a better model for the atom itself. Those theories we'll talk about later in the unit are known as the Heisenberg uncertainty principle, which talks about how it's difficult to measure the characteristics of an electron, and something else known as wave-particle duality, telling us that electrons are not simply particles traveling through space. All of this basically boils down to the fact that the locations and characteristics of an electron can only be predicted and not known. And because of that limitation, we have to change how we approach the actual model-making process itself. The end result is some very complicated mathematics that we'll definitely not be tackling this year, but the important thing to note is that these mathematics up here will ultimately result in a new picture of what an atom looks like down here. Now this is a model you probably haven't seen before in previous science classes, and from the complexity of what it is you're seeing, you can probably start to understand why. This model is difficult to work with, and you probably weren't ready for it until this point in your educational career. Just to summarize what we talked about in the video then, we basically have kind of outlined the process of going from the very simple Dalton model over on the left side, ultimately to the much more complex, but ultimately much more predictive and accurate Schrödinger model that we're going to develop on the right. We're going to spend the majority of this chapter focusing on the later models, but it's important to realize that all of these come from a historical context, and these discoveries didn't show up overnight. They're the result of a long process towards understanding the structure of an atom. To wrap things up for our video, let's get a list of things that you should be able to do as a result of what we talked about. You should be able to describe what basic atomic theory is, what's the goals of this process. You should be able to explain the purpose of an atomic model. Why is it important to have one? It allows us, again, to predict and understand the structure of an atom, which then allows us to predict and understand the behavior of that atom itself. And then finally, you should be able to briefly describe the history of the development of this model. As I just said, it didn't happen overnight. It's something that's developed through a series of discoveries and ideas, and you should be able to walk us through that process.